We want to design an approximation algorithm for the minimum vertex cover problem. And then we want to prove approximation guarantees for that algorithm. To design our algorithm, we will use something called the pricing method, which is a technique that can be used for the design of approximation algorithms for different problems. You have to modify the technique a little bit depending on the problem, but there's kind of a general idea behind it. In the vertex cover problem, each edge has to be covered by an incident vertex. And the intuitive idea behind the design of our algorithm is that we think of the edge as wanting one of the vertices to cover it, and the edge will pay a price to use one of its incident vertices. But several edges can be covered with just a single vertex if all those edges are incident to that vertex. So edges can join together to reach the price of that vertex. With this intuition, it would make sense that if we have a number of edges that have a single vertex as their common endpoint, then the total price that all of those edges pay together should not exceed the cost or weight of that single vertex, because the edges could just get together and pay for that vertex together. That's the intuition. So for every vertex, the total payments of edges incident to that vertex should not exceed the weight of that vertex. This is a fairness condition, otherwise the edges would be overpaying. Just based on this, we get a simple claim, which is that if you take any vertex cover of the graph, this can be any vertex cover at all, including the optimal one, and any fair prices for the edges, so we have a payment for each edge that satisfies in total the fairness condition we described earlier, then if you take all the payments of all the edges combined, then this cannot be larger than the total weight of the vertex cover. The proof of this claim is very simple. We sum up over all edges the prices those edges pay. What is a different way of enumerating all the edges? Well, if we have a vertex cover, it has a property that every edge has at least one of its endpoints in the vertex cover. So an alternative way of capturing all the edges would be to go through all the vertices in the vertex cover and look at all the edges that touch each of those vertices. Now, if you do this blindly, of course, we might enumerate some of the edges twice, because it's possible that in a vertex cover, an edge is indeed covered by both of its endpoints. But that will only give us an overestimate. So we will count some edges once and some other edges twice. The important part is we will never leave any edge out completely. Now we just need to plug in the inequality we get from the fairness condition, and that proves the entire claim. We will come back to this claim later. It's just for now important to recognize that this claim gives us effectively a lower bound on the cost of an optimal solution. This is because the vertex cover we are talking about in the claim can be the optimal vertex cover. And so if we have any fair pricing, then the payments the edges make, the total payments the edges make, will be a lower bound for the cost of an optimal weighted vertex cover. The idea behind our algorithm will now be to set the prices and simultaneously find a vertex cover. And ideally we want to do it in such a way that the prices are somewhat related to the cost of the vertex cover we find. Let me explain how the algorithm works using a concrete example. So here's a graph with 4 vertices, A, B, C, and D. And we also indicate the weights of each of those vertices. Now, in the beginning, our algorithm will start with all prices of the edges being equal to 0. That's the starting point. And also, in the beginning, we have not selected any of the vertices for our vertex cover yet. So in the beginning, we have not selected any vertex. So what we have is not really a valid solution because every single edge is uncovered. Now, since we need to cover all the edges, what we will do is the following. We will pick an edge that is not covered yet. So where both endpoints of the edge have not been selected for the vertex cover yet. It doesn't matter which uncovered edge we use, but in this example, let's say we pick the edge connecting vertex A to vertex B. We now start to increase the price of that edge. So we started at 0, and we will slowly increase it. And we will do this until we are risking to breach our fairness condition. So as you can see, once we reach a price of 3, what happens is that all the edges that are incident to vertex B have a price that sums up to 3, which is exactly the weight of that vertex B. And so if we would increase the price of the edge further than this, then we would breach the fairness condition. So this is a point where we stop. We call vertex B a tight vertex at this point because we have the property that the weight of the vertex is exactly equal to the prices of the edges incident to it. And once a vertex is tight, we include it in our solution. So it becomes part of our vertex cover that we are producing. So in this case, vertex B becomes tight, so we include it in our vertex cover, and it covers 2 of the edges in the graph, the edge connecting A to B and the edge connecting B to C. So there are 3 uncovered edges remaining, and we just repeat the process with one of those. So again, we pick one of the 3 remaining uncovered edges. Let's say, for this example, we will pick edge between A and D, and then we increase the price of that edge slowly until one of its endpoints becomes tight. So how far can we increase the price of the edge until this happens? You will notice that once the price of that edge gets to a value of 1, the vertex A becomes tight. This is because there is already an edge incident to it that has a price of 3, and now we add a price of 1 to it, and the weight of the vertex is only 4. So in this case, the weight of the vertex will be equal to the payments of the edges incident to it, and therefore vertex A becomes tight. We then include vertex A in our vertex cover solution, and it covers 2 of the remaining edges, namely the edge connecting A to D and the edge connecting A to C. And now there's 1 uncovered edge remaining, which is the edge connecting C to D. And we repeat the process again. We select that edge, we slowly increase its price until one of the 2 endpoints becomes tight. In this case, this happens when the edge has a price of 2, because vertex D now becomes tight. It has 1 edge connected to it that has a price of 1 and 1 edge that has a price of 2. So the weight of the vertex is 3, and so these 2 values are equal, so the vertex is tight. So we include that vertex in our vertex cover as well. So our final vertex cover is vertex A, vertex B, and vertex D. And we also produced prices for all the edges. 2 of the edges have a price of 0, 1 edge has a price of 1, 1 has a price of 2, and 1 has a price of 3. We can also write down some pseudocode of this algorithm I think the example I gave already illustrates the algorithm quite well, but just to make things complete, we can write down the pseudocode. So we would have something like the input is a graph and all the weights, and we go through all the edges and initialize the prices as 0. And then we go through the edges as long as there are edges that are not covered, and pick one, increase the price as long as it doesn't violate fairness. And then our vertex cover is simply the set of all the tight vertices in the end. It is clear that this algorithm is efficient. We are only iterating through all the edges of the graph, and then for each edge we determine how high we can set the price of that edge without violating the fairness condition, which can be easily done in polynomial time. So the only thing that remains to be shown is that this approximation algorithm achieves some approximation guarantee. And what we will show here is that this pricing method gives a true approximation for the minimum weighted vertex cover problem. The algorithm does indeed produce a vertex cover, so it produces a valid solution. The algorithm terminates because, well, in each iteration of the while loop, one more vertex becomes tight and is added to the vertex cover solution. So we have a limited number of vertices, which means we can only execute the while loop a limited number of times. So the algorithm terminates. On the other hand, what our final output is really a vertex cover. This is almost by definition of the while loop. As long as there's an edge that is not covered yet, we continue to execute the while loop and keep adding more vertices into our solution. So the while loop can only terminate once every edge is covered. So by definition of that while loop, the result of this algorithm is indeed a vertex cover. So the only thing that remains to be shown is how good this vertex cover is, what is the weight of that vertex cover, and how does it compare to the minimum weight possible that an optimal algorithm would produce. Say our algorithm produces a vertex cover, which is a set of vertices, let's call the set S. And let's think about what the weight of that set is. In other words, what the sum of the weights of the vertices in that set is. And one way of thinking about this is that our algorithm has the property that what is included in the set S are exactly the tight vertices. So the vertices that have the property that their weight is equal to the sum of the prices of the incident edges. So for this reason, we can rewrite this sum as being the sum of all these vertices. And then for each of them, we look at all the incident edges and sum up their prices. The next step is something quite extraordinary because it seems overly wasteful, but it turns out to be just the right thing. So we sum up over all vertices in the vertex cover here. But instead, we could sum up over all vertices in the graph, so potentially much larger set. And our claim is that this can only make this sum bigger. Clearly, this should be true because if we sum up over a larger set, the number can only increase that we get because all the prices are non-negative. So none of the prices are negative, and therefore, if we increase the size of the set that we sum over, the value we get will only increase. Now we have to look at this double sum and think about how often we will count each edge. So we are summing over the prices of edges somehow, but how often will we sum up over the price of one specific edge? And the answer is twice, because we sum up over all the vertices and then over all incident edges of that vertex. So what this means is we will encounter every edge twice because each edge has two endpoints. So we will encounter it once when we enumerate over the vertex that is one endpoint, and then we encounter it a second time when we enumerate over the vertex that's the other endpoint. So we are really only counting each edge exactly twice. And so what we get is that this double sum is just equal to 2 times the sum of the prices of all the edges. But we had already established that the sum of the prices of all the edges and the fair pricing forms a lower bound on the optimal cost for a minimum weighted vertex cover. So what we really have here is that this is bounded from above by 2 times the weight of an optimal solution. And if we chain all of this together, we see that the cost of the solution reproduce this vertex cover S is at most twice the cost of an optimal solution, which is what our claim was and which shows that our algorithm indeed gives a true approximation for our problem. So this pricing method is really quite useful in the design of certain approximation algorithms, in particular when it comes to graph type problems. And the other thing you should realize by now is that a crucial thing about designing approximation algorithms and proving guarantees about them is always that we need some form of lower bound for the optimal solution. So in this particular case, our lower bound was via these fair pricings. We established early on that if we have a fair pricing for the edges, then that total amount of prices of the edges is a lower bound for the optimal vertex cover cost. And you're always looking for something like this when we talk about approximation algorithms and proving approximation guarantees. You need some way of arguing about these optimal solutions, even when computing such an optimal solution might be hard and we might not really know very much about the structure of those solutions.